The Bermuda Triangle is a region of the western North Atlantic Ocean where multiple natural systems converge. In this area, the movement of ocean currents, the structure of the seafloor, atmospheric dynamics, and variations in Earth's magnetic field occur together in ways that are measurable and well documented. Each of these systems follows the known laws of physics and interacts with the others through continuous processes. The region is bounded by the southeastern coast of North America, the Caribbean islands, and the open Atlantic Ocean. Surface waters are generally warm, and the transport of heat northward through this portion of the Atlantic contributes to global energy redistribution. Ocean currents flow steadily, carrying mass and energy along predictable paths, while the underlying seafloor changes depth rapidly, creating gradients that influence the behavior of moving water. Above the ocean, the atmosphere responds to heat released from the surface. Differences in temperature and pressure drive the formation and movement of weather systems, which vary on daily, seasonal, and long-term timescales. These interactions between ocean and atmosphere are continuous and measurable, and they contribute to the dynamics observed throughout the region. The Earth's magnetic field also shows gradual variation in this area. The direction of magnetic north changes slowly over time and across space. These shifts can be mapped accurately with modern instruments, providing insight into the interactions between the planet's interior and its surface environment. Below the surface, temperature decreases with depth, pressure increases, and water density changes in layers. These vertical differences affect the speed of currents, the formation of waves, and the propagation of sound through the water. Methane hydrates, formed under specific pressure and temperature conditions in marine sediments, are stable in this environment, and their behavior is governed by the physical properties of the surrounding water and sediment. Taken together, these systems form a complex, continuous, natural environment. Each process operates according to physical laws, interacting with the others in predictable ways. Understanding the region requires careful observation and measurement. In the following sections, each system will be described in detail, beginning with the geographic structure of the area. The geography. The Bermuda Triangle occupies a portion of the western North Atlantic Ocean, roughly defined by the points of Miami, Bermuda, and Puerto Rico. Within this triangular area, the ocean stretches across hundreds of kilometers, shifting in depth and character as it moves from the shallow continental shelves near the Bahamas to the open, deep Atlantic waters. The surface itself appears smooth from afar, yet beneath, the seafloor rises and falls, forming a complex network of plateaus, slopes, and trenches. To the north and west, the region meets the continental shelf of North America, where shallow waters gradually give way to the steep slopes of the Atlantic seaboard. These slopes descend into deep basins, creating a rapid transition from hundreds of meters to several kilometers in depth. Near Bermuda, the ocean floor consists of a series of plateaus and ridges, interspersed with depressions and valleys, each influencing the flow of water above it in subtle but measurable ways. Off Puerto Rico, the sea drops even more abruptly, forming part of the Puerto Rico Trench, one of the deepest sections of the Atlantic Ocean. The spatial arrangement of islands, shoals, and banks adds further complexity. The Bahamas, with their shallow banks and extensive coral structures, create areas where water circulation slows and forms eddies. These shallow regions contrast sharply with the adjacent deep ocean basins, producing gradients in temperature, pressure, and salinity that ripple through the surrounding waters. In combination, the landforms and underwater structures define pathways for currents, guide the movement of heat, and shape the interaction between surface and deep water. Latitude and position within the subtropical Atlantic also influence environmental conditions. The region lies within the trade wind belt, receiving consistent wind patterns that interact with the warm surface waters. Seasonal shifts in wind direction and intensity, combined with the varying depth of the ocean, contribute to the formation of waves and the circulation of energy across the surface. These geographic factors set the stage for the complex processes that follow, from magnetic variations to thermohaline layering and weather dynamics. Overall, the geography of the Bermuda Triangle is defined by both its surface and subsurface features. The combination of islands, shoals, plateaus, trenches, and continental slopes creates an environment where water, air, and energy interact continuously. Each feature contributes to the measurable patterns observed in ocean currents, atmospheric movement, and the physical properties of the water column. Understanding this geography is essential for describing the natural processes that occur in the region, providing the foundation for examining magnetic phenomena, ocean currents, and other scientific systems in the sections to follow. Magnetic phenomena. The Bermuda Triangle region is notable for exhibiting measurable differences in the Earth's magnetic field compared to surrounding areas. These differences arise from a combination of processes occurring both deep within the planet and in the oceanic crust above. One primary factor is the behavior of the geomagnetic field itself. The field is generated by movements of molten iron and other metals in the outer core. These movements are dynamic and non-uniform, producing small variations in intensity and direction across different parts of the globe. In the Bermuda Triangle region, these field lines shift along slightly more complex paths than in neighboring areas. This process, known as secular variation, occurs slowly over years and decades, gradually changing the angle and strength of the field. Although the changes are subtle, they are consistent and measurable, forming a predictable pattern over time. A second contributing factor is the composition of the oceanic crust beneath the area. The seafloor is composed of multiple types of rock, some containing higher concentrations of iron and other magnetic minerals. These materials locally alter the orientation and strength of the magnetic field, creating small-scale crustal anomalies. These anomalies are confined to specific regions and are typically only detectable using precise instruments, yet they combine with the global geomagnetic field to produce measurable deviations. Modern magnetometers on ships and satellites can map these variations with high resolution, allowing scientists to study both the broader patterns of the Earth's field and the local anomalies caused by the crust. The combination of secular variation and crustal anomalies produces a magnetic environment that differs from other areas of the Atlantic Ocean. Compasses operating in this region may point a few degrees off from true north if local declination is not accounted for. This effect is a natural result of the physics governing the Earth's magnetic system and does not indicate instability or malfunction. Navigational charts provide corrections for these variations, and modern GPS technology fully compensates for them, ensuring accurate navigation. In addition, these variations influence the propagation of low-frequency electromagnetic signals over the ocean. Signals can bend slightly or experience minor changes in strength depending on the local orientation and intensity of the magnetic field. These effects are predictable, measurable, and fully understood by scientists, providing further evidence that the field behaves according to established physical laws. Overall, the magnetic field in the Bermuda Triangle is subtly distinct due to the combination of slow, core-generated changes and local crustal effects. These variations are continuous, predictable, and well mapped. Understanding them offers insight into the structure and dynamics of the Earth's interior, as well as the interactions between the magnetic field, the ocean, and the atmosphere above. The region's magnetic characteristics provide a foundation for examining the other natural systems that interact here, including currents, weather patterns, and seafloor dynamics. By studying these phenomena, scientists can observe how interconnected forces shape the environment in this part of the Atlantic Ocean. Ocean currents. The Bermuda Triangle is located within a region of the Atlantic Ocean where several major currents intersect and flow in complex, continuous patterns. The movement of ocean water in this area is influenced by a combination of wind, temperature, salinity, and the shape of the seafloor. These factors together create a dynamic environment in which water circulates steadily, transporting heat, nutrients, and energy across large distances. One of the dominant currents in the region is the Gulf Stream. Originating in the Gulf of Mexico, it flows northeast along the eastern coast of North America before moving into the open Atlantic. This current carries warm surface water from the tropics toward higher latitudes, contributing significantly to the redistribution of heat across the planet. As the Gulf Stream passes through the Bermuda Triangle, it interacts with local features such as islands, banks, and seafloor slopes. These interactions influence the speed and direction of the flow, producing measurable variations in current intensity and creating areas of convergence and divergence in the water. In summary, the Bermuda Triangle's ocean currents form an interconnected system shaped by wind, temperature, salinity, and the underlying seafloor. Surface and deep currents flow together, layered and interacting, producing predictable patterns of energy and water movement. Understanding these currents provides insight into the region's physical environment and sets the stage for examining other natural phenomena, including thermohaline structure, weather patterns, and wave dynamics. The continuous motion of water here is a demonstration of the physical processes governing the ocean and its role in the broader Atlantic system. Weather patterns. The Bermuda Triangle region experiences consistent and measurable atmospheric processes. Weather in this area is shaped by the interaction of temperature, pressure, humidity, and wind, all of which are governed by well-understood physical laws. These forces combine to produce a range of predictable weather patterns that vary seasonally and daily, yet remain part of a continuous natural system. One of the primary drivers of weather in the region is the transport of warm surface water from the tropics. As water absorbs solar energy, it releases heat into the atmosphere, influencing air temperature and pressure. Warm air rises, creating low-pressure zones that drive the movement of surrounding air masses. These movements generate steady trade winds that blow consistently from the east in subtropical latitudes, interacting with other wind systems to shape surface pressure and storm formation. Seasonal changes also influence atmospheric patterns. During the summer and early fall, the Atlantic experiences increased solar heating, which strengthens the trade winds and promotes the development of tropical storms and hurricanes. These systems follow predictable paths influenced by the Coriolis effect, the distribution of pressure systems, and the position of high-pressure zones. Their intensity and movement are measurable and modeled accurately by meteorologists based on the underlying physics of heat, moisture, and fluid motion in the atmosphere. The interaction between the ocean and atmosphere is continuous. Warm waters contribute to evaporation, adding moisture to the air and influencing humidity levels. Higher humidity affects cloud formation, precipitation, and the development of localized weather systems. Wind patterns, in turn, influence ocean currents, creating feedback loops in which air and water shape each other's movement. These processes occur without interruption, forming a self-regulating system that governs conditions throughout the region. Local geographic features also have measurable effects on weather. Islands and shallow banks can alter wind flow, redirecting air masses and creating areas of slightly different temperature or pressure. Such variations influence cloud development and the distribution of rainfall. Over open water without obstruction, the winds and currents maintain steady patterns, while near coastal regions, minor deviations can be observed. All of these effects are fully understood and can be measured and predicted using modern instrumentation. Atmospheric pressure, temperature, and humidity are closely monitored in the Bermuda Triangle. Satellites, buoys, and research vessels provide continuous data, allowing precise modeling of weather systems. These measurements confirm that, while storms may be strong, their formation follows known physical processes. No unusual or unexplained atmospheric forces are present. All observed phenomena result from heat transfer, fluid dynamics, and the rotation of the Earth. In summary, the weather patterns in the Bermuda Triangle are the product of predictable interactions between oceanic heat, atmospheric motion, and geographic features. Surface winds, trade winds, and seasonal shifts create measurable and consistent systems that influence temperature, pressure, and precipitation. The interaction between warm surface waters and the atmosphere drives local convection, cloud formation, and storm activity, forming a continuous, observable, and explainable meteorological environment. Understanding these patterns provides insight into how energy moves between the ocean and atmosphere, shaping both the weather and the oceanic currents that pass through this region of the Atlantic. Methane hydrates. Beneath the seafloor of the Bermuda Triangle region, specific chemical and physical conditions allow the formation of methane hydrates. These compounds are crystalline structures in which methane molecules are trapped within cages of water molecules. Methane hydrates form when temperature, pressure, and gas concentration fall within precise ranges, typically found in sediments on the continental slope and deeper basins. Their stability is entirely dictated by physical conditions and the laws of chemistry. Methane hydrates are concentrated in regions where organic matter has accumulated in the seafloor sediments. Over time, microbial decomposition of this material produces methane gas. When this gas encounters the high pressures and low temperatures of deeper sediments, it becomes trapped in ice-like structures, forming hydrates. The depth and temperature of the seafloor in the Bermuda Triangle provide suitable conditions for their formation. Shallow areas, such as banks and plateaus, may have fewer hydrates, while deeper basins support more extensive deposits. The stability of methane hydrates is sensitive to both pressure and temperature. Any significant change in either factor can cause the solid structure to dissociate, releasing methane gas into the surrounding water. In the deep waters of the Bermuda Triangle, pressure is sufficient to maintain hydrates in a stable state under normal conditions. Temperature variations at these depths are minimal, further ensuring that the compounds remain solid. Scientists can measure these conditions directly and model hydrate stability with precision. Methane released from hydrates can influence water density locally. Methane bubbles that reach the water column reduce the overall density of the surrounding water, which can affect vertical movement and mixing. In extreme cases, rapid gas release could alter the buoyancy of water layers temporarily. However, such events are rare and occur under specific measurable geological conditions. The presence of hydrates does not represent a continuous hazard. It is simply a part of the natural, chemical, and physical environment of the sea floor. Hydrate deposits are mapped using seismic surveys and submersible instruments, allowing researchers to locate areas of concentrated methane. These studies show that the distribution of hydrates is irregular, corresponding to variations in sediment type, organic content, and depth. The interaction between hydrates and surrounding water is governed entirely by physics. Pressure, temperature, and density determine the behavior of both the solid structures and any gas that may be released. The presence of methane hydrates in the Bermuda Triangle demonstrates the complexity of the region's subsurface environment. They are an example of how chemical, thermal, and pressure conditions combine to produce stable, measurable compounds beneath the ocean floor. Understanding their formation and stability provides insight into broader processes of sediment chemistry, ocean density stratification, and energy transfer within the water column. Hydrates are not anomalies or hazards by themselves. They exist as a normal component of deep-sea geology, responding predictably to the conditions that surround them. In summary, methane hydrates are stable crystalline compounds formed under specific temperature and pressure conditions within the sediments beneath the Bermuda Triangle. Their formation, distribution, and potential interactions with the water above are entirely dictated by measurable physical and chemical processes. Studying these deposits helps scientists understand subsurface chemistry, vertical water column dynamics, and the intricate balance of energy and matter in this part of the Atlantic. The presence of hydrates adds another layer to the region's natural observable systems, each operating according to known laws of physics and chemistry. Rogue waves. The Bermuda Triangle region is part of the Atlantic Ocean, where surface conditions and underlying currents occasionally combine to produce exceptionally large waves, commonly known as rogue waves. These waves are not supernatural or unpredictable. They are the result of well-understood physical processes governed by the interaction of wind, ocean currents, and wave dynamics. They are distinct from typical ocean waves due to their sudden appearance, extreme height, and concentration of energy. Rogue waves form primarily through constructive interference. In this process, multiple wave systems traveling in different directions can align temporarily, causing the peaks to combine and produce a wave significantly taller than the surrounding waves. In the Bermuda Triangle, the intersection of the Gulf Stream with other ocean currents can create conditions favorable for such alignment. These currents affect the speed and direction of waves, allowing energy to concentrate in a single steep wave. The process is entirely physical and can be modeled mathematically using the principles of fluid dynamics. Wind patterns also contribute to rogue wave formation. Strong, sustained winds generate waves over long distances, a phenomenon known as fetch. When wind-driven waves encounter opposing currents or intersecting swell systems, the energy can focus in certain locations, increasing wave height locally. In the Bermuda Triangle, the interaction of trade winds, seasonal storm systems, and the Gulf Stream creates areas where waves may grow higher than in the open ocean nearby. These conditions are measurable and predictable, though the exact location and timing of individual rogue waves are naturally variable due to the complexity of wave interactions. Depth and seafloor topography play additional roles. Steep continental slopes, underwater ridges, and trenches can influence wave behavior by modifying the speed and direction of currents beneath them. When surface waves travel over such features, they may become compressed or refracted, amplifying wave height. These interactions are governed by the physical laws of wave mechanics and are observable using oceanographic instruments. Rogue waves also differ from normal waves in their steepness and energy density, while typical waves are limited by wind strength and water depth. Rogue waves concentrate energy from multiple sources, forming peaks that are significantly higher than the surrounding sea state. This concentration is temporary and local, dissipating as wave systems move and interfere with other waves. Scientific measurements using buoys, satellites, and radar confirm their height, frequency, and distribution. Although rogue waves can be extreme, they are natural events explained entirely by ocean physics. They do not occur continuously in a single location. Rather, they appear sporadically when multiple physical factors align. Their study provides insight into the interactions of currents, wind, and waves, demonstrating how energy moves through the ocean in complex but predictable ways. In summary, rogue waves in the Bermuda Triangle are the result of overlapping currents, intersecting wave systems, wind patterns, and seafloor topography. They are measurable, predictable within statistical models, and governed by known physical laws. These waves represent the dynamic energy of the ocean, concentrated briefly in localized areas, and they contribute to the overall complexity of the region's marine environment. Understanding their formation and behavior enhances our knowledge of ocean dynamics, wave mechanics, and the continuous interplay between currents, wind, and water in this part of the Atlantic. The waters of the Bermuda Triangle flow in quiet, measured rhythms, guided by currents, waves, layers, and magnetic patterns. Each movement is part of a larger, continuous system, a dance of natural forces unfolding beneath the surface. The ocean rises and falls, the layers shift, and the currents glide steadily, all governed by the gentle laws of physics and chemistry. Observing these processes reminds us of the harmony and order present even in the vast deep waters of the Atlantic. Although rogue waves can be extreme, they are natural events explained entirely by ocean physics. They do not occur continuously in a single location. Rather, they appear sporadically when multiple physical factors align. Their study provides insight into the interactions of currents, wind, and waves, demonstrating how energy moves through the ocean in complex but predictable ways. In summary, rogue waves in the Bermuda Triangle are the result of overlapping currents, intersecting wave systems, wind patterns, and seafloor topography. They are measurable, predictable within statistical models, and governed by known physical laws. These waves represent the dynamic energy of the ocean, concentrated briefly in localized areas, and they contribute to the overall complexity of the region's marine environment. Understanding their formation and behavior enhances our knowledge of ocean dynamics, wave mechanics, and the continuous interplay between currents, wind, and water in this part of the Atlantic. The waters of the Bermuda Triangle flow in quiet, measured rhythms, guided by currents, waves, layers, and magnetic patterns. Each movement is part of a larger, continuous system, a dance of natural forces unfolding beneath the surface. The ocean rises and falls, the layers shift, and the currents glide steadily, all governed by the gentle laws of physics and chemistry. Observing these processes reminds us of the harmony and order present even in the vast, deep waters of the Atlantic. If you have enjoyed this journey through the scientific wonders of the Bermuda Triangle, take a moment to subscribe to the channel and share your thoughts in the comments below.